So let us start this class. Good afternoon, everyone. And this is lecture number 19. And electrostatics has gone a long way. And probably at this day today, we probably might end up this particular section of electrostatics. So from tomorrow, I'm planning to start your next topic, which is capacitance. Anyways, previous class, I think I had to given you some important notes about what about self energy of a sphere and self energy of a conducting sphere and self energy of an insulating sphere. Do we remember this? And I also told you how to find out how to use this self energy in various questions. We had done a couple of questions where we had found out the self energy of two spheres or two shells. And remember, these type of questions are in fashion these days. And I expect that you might get one or two of these questions, these shell wala questions. Now I'll try to cover all of them, whatever is possible. We also discuss the concept of energy density, half epsilon E square. Wherever in space there is electrostatic field, there is energy stored. How much energy is stored in unit volume is known as energy density. And I think I gave you this question to solve. I think we had done it in the class as well. It was from SCV. I think you have solved it. Yes or no? Huh? Huh? Solved it or not? Silence? What happened? We solved it? Energy stored in a small cubical volume. Did we do it or not? Everyone seems to be on a different dimension altogether. Are we here all? Everyone? Same universe, same dimension. You can hear me, you can see me. Or my voice is going in some other dimension. Everyone is there, no?
No, sir.
Sir.
What, sir? No, sir, you are not there.
Yes, sir.
My voice is getting to you, no? You are in the same dimension.
Yes, sir.
3 dimension of space and 1 dimension of time. Okay, good to know that. We're in the same dimension, same universe. The next heading that we are going to do in this universe is known as electrostatic pressure. I don't know whether you have heard this term, but some very tricky problems in electrostatics are from this particular topic, which is known as electrostatic pressure. Now, what is this electrostatic pressure? Wherever you have a conductor and a conductor is having charge, you remember that conductor. Whenever you give charge to a conductor, that charge comes on the outer surface of the conductor. Now, because of this charge, the conductor is going to create electrostatic field, and because of that field, the conductor is going to experience some force, and because of that force, that is going to experience electrostatic pressure. We are not going to get into details of how we understand this, but this is a fair diagram that if you take a small element ds on the surface of a conductor, the small element ds experiences a pressure, and if you multiply it by the area of this area will experience a force, and that force will be in the perpendicular direction. You must understand pressure does not have any direction, but whenever pressure is applied on a surface, the surface experiences force in the perpendicular direction. Do we know this? Yes or no?
Yes, sir.
So what is the electrostatic pressure? Electrostatic pressure on any surface of conductor is given by this legendary formula, sigma square by 2 epsilon naught. What is sigma here? Huh?
Surface charge density, sir.
Surface charge density, and this electrostatic pressure will be equal to small force dF divided by small area element ds. So if they ask you to find out the force on the surface of this conductor, what you got to do is you have to find the integral of sigma square by 2 epsilon naught into ds. But that integral is not easy to calculate. For this particular case, it might be easy because the angle and the electrostatic force might be same, but if the question is very difficult, the force becomes very difficult to calculate, but you must know how to calculate it. Got this? We will use this formula and calculate force, electrostatic force between two conductors. If everything goes fine, probably by the next or the next class, we will be doing it. This is known as electrostatic pressure. I've written electrostatics pressure. It is electrostatic pressure. Okay. Note this down, fatafat. We don't have time that we can lose. So note down the heading electrostatic pressure, draw the diagram, write the answer, and stay happy.
Sir.
Okay.
Completed, sir.
Okay. Again, these are small things. I'm trying to cover everything that is possible. I'm trying to do each and every small point so that any question comes from that small point, no one else probably would be able to do it unless and until you know it. The next thing is a small heading which is known as equilibrium of a soap bubble. Now I don't know whether this surface tension was covered for you. Was it covered? Surface tension? Have
Yes,
you
sir.
have you done the topic on surface tension? Yes or no?
Yes, sir.
Well done. When did you do it? I thought that it is not covered.
Fluid mechanics, sir.
Your fluid mechanics have been covered. Yes or no?
Sir.
Well, that is great. Then, if that thing is covered, then probably you will be able to understand this in a better way, probably. So, the soap bubble is normally spherical in shape. We take it spherical in shape. All of us understand this.
Yes, sir.
If this soap bubble is charged, if this soap bubble is charged, then what will happen? If this soap bubble is charged, now there is a difference of pressure between the inside and the outside. Everyone knows this, yes or no?
Yes, sir.
Where is the pressure more, inside or outside?
Inside out, sir.
Where is the pressure more, inside or outside?
Sir.
Inside, sir. And you must also know the difference in pressure between inside and outside. How much is inside is more? Eh? On which
Outside.
side is the pressure more? It is always more on the concave side. Do we remember concave, convex, concave, convex? Yes or no?
Yes,
Huh?
sir.
Right now it is on the concave side. So concave side is inside, therefore the pressure inside is more. Now the pressure inside is more, and you can write the equilibrium condition. So this is the equilibrium condition. I am not going to, when you know it. So if someone asks you a question on this is the pressure on the concave side right now. Pressure inside will be pressure outside plus 4T by R minus sigma square by 2 epsilon naught. You understand how this sigma square by 2 epsilon naught has come? Yes or no? Huh?
Yes, sir.
Sir.
Ah. So the difference in pressure, excess pressure, becomes pressure inside minus pressure outside, which is the excess pressure. And this excess pressure can be written as 4T by R minus sigma square by 2 epsilon naught. I hope everyone is following me what I'm saying. Yes or no?
Yes, sir.
Okay. Now, if this soap bubble is in equilibrium, pressure inside and pressure outside must be same. Yes or no?
Yes, sir.
So if pressure inside and pressure outside is same, then my dear friends, you will have this legendary equation coming into the picture. Remember this equation? A typical question on this equilibrium of soap bubbles will come based on this equation, and the equation is pretty damn simple. 4T by R is equal to sigma square by 2 epsilon naught. Sigma square by 2 epsilon naught. I hope everyone has understood this. Yes or no?
Yes, sir.
Now doing a jiggery piggery of all this. You understand the meaning of jiggery piggery? Upar niche upar is known as jiggery piggery. So if you do a jiggery piggery of this formula, you can find out the various results that I am going to show you, and you need to just note them down. For example, the radius of the soap bubble, do a jiggery piggery of 4T by R is sigma square by 2 epsilon naught. You can find out the radius of the soap bubble. So anything they can ask. They can ask you the radius of the soap bubble. They can ask you the value of surface tension. So everything basically comes from that equation that I have written. I hope you have understood this. Yes or no?
Yes, sir.
This is the second formula. What is the surface tension? These are the most typical type of question that are asked in JEE because it mixes two topics. Here, fluid is mixed with electrostatics. Here, fluid is mixed with electrostatics, and that is why the question starts to look a lot difficult than it actually is. Then they can ask you what is the total charge on the soap bubble. So basically you find the value of sigma and you multiply it by 4 pi r square. Do we understand this?
Yes, sir.
And the last one of this lot, I will put it downwards because it will not be coming here. I think I will put it here. The last one of the lot is the value of electric field on the surface of a bubble. Remember, all these formulae, they have come from just one formula, which is 4T by R is sigma square by 2 epsilon naught. So jiggery piggery of all this. In one case, we have found out the surface tension. In the second, we have found out the radius of the bubble, and so on. Are we noting it down or chilling out? Eh?
Done, sir.
Then,
Noting,
sir,
sir.
one more
Wait,
formula,
sir.
sir. Potential on the surface. Because it is a sphere, so they can ask you both the things. They can ask you electric field. They can ask you the electric potential. So this is the formula of potential. I have made a note of it, put it in a PDF, safe and secure, and I am using that same research of mine. There is no point wasting in getting the derivation of it. I have already shown you the derivation. How does the derivation look like? And that is how things stand. Okay. Have you noted this down? Yes or no?
Noted,
All these
Yes, sir.
formulas are there in the safe, right? Huh? Or not?
Done, sir.
Okay. That takes us to the next heading. And the next heading is this. Properties of a conductor. Properties of a conductor. Properties of a conductor. What are the properties of a conductor? We have come across some of these properties before. Almost all the properties of a conductor we have come across at some point in life during the discussion of around these 18 or 19 classes that we have had. But now we'll try to assemble them all and put them at one place. And the first property, it's not a property. Charge of an isolated conductor. What will happen to the charge of an isolated conductor? Huh? This is the first thing that I told you in first class. Charge of an isolated conductor? Huh?
0, sir.
0, sir. Charge of an isolated conductor remains constant. a conductor is charged and it is isolated, nothing in the universe can change the charge. Charge of an isolated conductor remains constant, not zero, beta. You understand this? Huh?
Yes, sir.
Yes, sir. Once I write, then everyone understands. 5 minutes after that, everyone forgets. Everyone is competing. Who is the bigger Gajini? Who can forget things faster? Everyone is competing against each other. I am the biggest Gajini. I am the biggest Gajini. Okay. Second thing, conductors are what? Conductors are nothing but materials which has a large number of electrons which can freely move ding 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 like this. We understand this, yes or no?
Yes,
Huh?
sir.
Yes.
Inside a conductor, the value of electric field is zero. Do we understand this?
Yes, sir.
Inside a conductor, electric field is zero. Now, since electric field is zero, then what will happen? Electric lines of force. If you place it in a uniform field, the lines of force will not enter a conductor. Do we remember this? Huh? Electric lines
Sir.
of force cannot cross a conductor. Okay. Then if they don't cross on a conductor, then what will happen? They will either terminate on the conductor or they will emerge out from the conductor. Whether they terminate or whether they emerge out, they will always terminate or emerge out in what direction?
Perpendicular, sir.
Hey, you remember this? Great, great, great. As means electrostatic is getting to our heads. That's good. They will always terminate or emerge out perpendicular to the conductor. Now, since we are talking about conductors and all of these things are related to each other, a conductor, electric field is zero, my dear friends. So if electric field is zero, then all the conductors, all the surface of the conductor will become what type of surface? Will become equipotential surface. Yes or no?
Yes, sir.
Huh? Now, whenever someone talks about potential of a conductor, is equal to potential on the surface of the conductor, and that will be same as potential inside the conductor. Do we understand this? So you can find out whatever is convenient to you. Sometimes finding the potential on the surface might be convenient. Sometimes to find the potential on the center of the conductor in case of a spherical conductor can be easier. We don't have to look for tougher way. We have to look for the easier way. Do we understand this? Huh?
Yes, sir.
Huh? We have to look for the easier way where we can find the potential easily. So that is the place you find out the potential. Now, since there is no electric field inside the conductor is equipotential and so on. Therefore, we have charges cannot remain inside the conductor. They will always come where?
Yes.
They will always come on the surface of the conductor. So that is the next point. Charge will only come on the surface of the conductor. Do we understand it? Or is it going above or saying bye bye? Sir, bye bye हो गया, bye bye. हैं? Bye bye. Bye bye.
Understood, sir.
Okay. Now, since we have talked about the electric field outside a conductor, and comes a very important point. What will be the value of electric field just outside a conductor, any any size, any shape? what will be the electric field intensity just outside the conductor? And the answer is sigma by epsilon naught. Do we understand this? And this eta vector is telling us that it is perpendicular to the surface of the conductor. I hope everyone is noting down everything. Yes or no?
Yes,
Sir.
sir.
Now, if the conductor is of uniform shape, sigma will be uniform. But if the conductor is not of uniform shape, then what will happen, my dear friends? If the conductor is of a ulta seedha shape, say for example, the conductor is like this, ulta seedha shape. If the conductor is of ulta seedha shape, like this, the charge density will not be uniform. Where will you have more charges and where will you have less charges? Sharper points will have more charges and blunt will have less charges. Do we understand this? So surface charge density on the surface of a conductor is inversely proportional to the radius of curvature. Where the radius of curvature is more, means it is flatter. The charge density is less. Where it is sharp, sharp edges, sharp edges, you will have more surface charge density. Do we understand this?
Yes, sir.
Huh?
Yes, sir.
Please note down everything. Now, since here in this case, as you can see, surface charge density is different at different points. Therefore, the electric field will also be different at different points. At point A, electric field will be sigma A by epsilon naught into eta vector. Eta vector is the unit vector which is perpendicular to that surface at that point. I hope you understand this. Yes or no?
Yes, sir.
Okay. Now, what will happen if you connect two conductors by a conducting wire? And this thing is going to come in the next chapter very predominantly. What will happen when you connect two conductors by a conducting wire? What will happen when two conductors are connected by a conducting wire? There will be a flow of charge. And how long will the charge flow? How long will the charge flow? Always till infinity. How long will the charge flow?
Till their potentials become equal.
Until the point their potentials become equal. So if you want the charge flow to remain continuous, you must have something. And what is that something? We will understand that something in the next chapter. So when two conductors are connected, there will be a charge flow unless and until the time where their charges, where their potentials become zero. No, the potentials become equal. Do we understand this?
Yes, sir.
The next thing is what will happen if you connect a conductor to earth. You connect a conductor to earth. We call it grounding. This is how grounding is shown. Do you know this?
Yes, sir.
We say that its potential becomes zero. Why do we say that its potential becomes zero? Because we say that its potential becomes equal to the potential of earth, and earth is a very large conductor. Connecting small things may not change its potential. So we take the potential of earth as zero, and therefore we take the potential of the conductor also as zero. Do we understand this?
Sir.
Now, when you connect a conductor to earth, and if the conductor is isolated, it is not connected to anything, not in contact with anything, then the charge on the conductor in fact will become zero. When an isolated conductor, not connected to anything, isolated from the surroundings, it is connected to earth, its charge is going to become zero. I hope everyone is understanding this and writing these points. The next point is about electrostatic pressure. We have already discussed that point, but still. Electrostatic pressure on the surface of a conductor is sigma square by 2 epsilon naught. I'll give you 2 minutes to note everything down. So we move ahead. Up till now, we had seen some general properties about conductor. Now we come to the most interesting and the important ones. What are the most interesting, more interesting and important ones? When we have a cavity inside a conductor. Cavity inside a conductor. What do you understand by cavity? Huh?
Yes, sir.
Cavity means hollow space. Up till now, what we were discussing were solid conductors. They were all material everywhere. Now, if the material is not there, if there is a cavity inside a conductor, then my dear friends, what will happen? If there is a cavity inside a conductor, then what will happen? Yes? Any idea? What will happen if there is a cavity inside the conductor? And if I give a charge to the conductor, where will it come on the conductor?
Yes, sir.
Huh?
Surface, sir.
It will always come on the surface, sir. It will never come on the cavity, sir. It will always come on the surface. And which surface? It will always come on the outer surface. Do we understand this? Even if there is a cavity inside a conductor, you charge that conductor, the charge will always come on the outer surface of the conductor. Do we understand this? Yes or no?
Yes, sir.
So if I'm not getting a diagram, looking for a diagram, if I can get a diagram to help you understand conductor with a cavity. Conductor with a cavity. Where can I get a diagram of conductor with a cavity? Okay, if I'm not getting a diagram, I will draw my own. This is the conductor. Ding, 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 ding. And it has a cavity. Ping, 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 ping. So here it is solid. And in between there is liquid. I mean, when I say liquid, I mean it's a hollow space. Now, if I charge this conductor, no matter what shape, the charge will only come on the outer surface of the conductor. And since I have drawn this conductor as non-uniform conductor, therefore the charge distribution would be non-uniform. If it was a uniform conductor, the charge distribution would be uniform. Do we understand this? Yes or no?
Yes, sir.
Sir.
Sir? You understand this, sir? So even if there is a cavity inside the conductor, the charge will come on the outer surface of the conductor. Now the thing comes, if I charge a conductor, even with a cavity, charge will come on the outer surface of the conductor. But if I now place a charge inside the cavity, placing a charge and charging the conductor is different. Charging the conductor means you charge it, you remove electrons or whatever, charge will come on the outer surface. Putting a charge means I am going to put a point charge inside the cavity. What will happen if I put a point charge or a charge inside cavity? What will happen if I put a charge inside the cavity of a conductor? Yes. So this was case number 1. And what comes here is case number 2. And we'll try to analyze both the cases side by side. I hope you can see both the cases, case number 1 and case number 2. What is the difference between case number 1 and case number 2? So in this second case, what I have done is I have a isolated conductor. I have a conductor and I have put a point charge inside the cavity of the conductor. Now because of this point charge, can you see this point charge? This pink fellow. Do you see this point charge? Yes or no?
Yes, sir.
So this is the point charge I have put. Now, because of this point charge, what happens, my dear friends? A negative charge will come on this cavity, on the surface of this cavity. Do we understand this? Do we understand this?
Yes, sir.
And since the charge of this outer conductor, I did not give it any charge, so the total charge of this conductor should remain constant. Total charge of this conductor should remain 0. Since minus q has appeared on the green surface, there will be a plus small q charge appearing on the outer surface. Do we understand this? So this is how the charge will come. Are we able to understand this, or this is going above and saying bye bye?
Understood.
Huh? Bye bye.
Understood, sir.
Okay, so if you put a charge inside the cavity of the conductor, because of that charge, equal and opposite charge will be coming on the inner surface of the cavity, and same charge will be appearing on the outer surface of the cavity. Is this point clear to everyone?
Yes, sir.
Yes, sir, or no, sir?
Yes, sir.
Yes, sir. Then comes the third case. Have you noted down the second case?
Yes, sir.
Third case is a cousin brother of the second case. Shall I move on to the third case? Anybody noted down the second case?
Yes, sir.
The third case is the cousin brother of second case. In the third case, what I have done, I have given this conductor a charge plus capital Q. Plus capital Q is already there. So this plus capital Q will appear on the outer surface. Yes or no? Huh?
Yes, sir.
Then I have put this small fellow plus small q inside the cavity. Now because of this small q inside the cavity, on the inner surface you will have minus q, and on the outer surface you will have plus q because of the cavity charge, and the outside charge is already plus capital Q, so the total charge becomes q plus capital Q. We understand this?
Sure.
Now it is going above and it's saying bye 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 bye. Do we understand this, bacha?
Understood.
Sir, repeat again, sir.
What do you want me to repeat, beta?
Yes, sir.
So this case is same as case number 2. The only thing that is different is I have given this conductor charge plus q. So plus q is already there on the conductor. It will come on the outer surface. Then I have played a charge inside. Because of the inside charge, same thing happens as case number 2. The total charge on the outer surface becomes small q plus capital Q. You understand this?
Sir.
Same thing. Only plus q charge is already there on the conductor. In the second case, there was no charge on the conductor. In the third case, there is a charge on the conductor. You got this?
Yes, sir.
That is the only difference between case number 2 and case number 3. Case number 4 is a simpler one. There is nothing inside the cavity. There is nothing inside the cavity. Nothing happens. Nothing happens. Everyone stays as they were. So this is simple to understand. There is nothing inside the cavity. Nothing happens. And the results remain same. Do we understand this? Huh?
Yes, sir.
पक्का सर? वो कच्चा
पक्का,
पक्का
sir.
सर? पक्का पक्का और कच्चा पक्का?
Paka paka, sir.
Okay. Good. Now comes the most important aspect of this. The most important aspect of this. Have you understood this? What we have done here up till now?
Sir.
Oh, this has gone above that saying bye bye. Bye bye, sir. I'm going. Bye bye, sir.
Understood, sir.
Then comes the most important aspect of this property of conductor. I think this is point number 5 or
Show
6.
previous slide, sir.
Yes, beta?
Show previous slide.
Arey. There was nothing in the previous slide, bhai. On the fourth case, the charge was 0. Okay, draw it. Once you are done, let me know. Then we move on to the next case, which is the most important case. And this case is also known as electrostatic shielding. Now, what is this electrostatic shielding? Now, you can see here, this is the conductor of case number 3, where you have a point charge placed inside the cavity, and you have a charge capital Q on given to the conductor. So the total charge on the outer surface of the conductor becomes Q plus capital Q. Everyone understands this?
Sir.
Now, because of this charge at the center, I have this green charge coming on the inner surface, minus Q, yes or no? And because of this minus Q, I have plus small q on the outer surface, and that is how things go. Now, what does this principle say? That if I take any point C, which is outside this conductor, if I take any point C, which is outside the conductor, the only charge that is going to create field at this outer point is charge coming on the outer surface. So whatever is charge on the outer surface, that charge is only going to create field for outside points. Do we understand this? Yes or no?
Yes, sir.
For outside points, electric field is created by only outside charges. Therefore, the field created by any inside charge at any point outside would be 0. Do we understand this?
Yes, sir.
So if you understand one thing, then you take the vice versa of that thing. What will be the vice versa of that thing? So basically what I want to say, I can say it in 3 different ways. Way number 1, field outside conductor, is only due to which charges? Huh?
Outer charge.
Outer charges. Outer, which are on the outer surface. Outer surface. That means field outside conductor due to inner charges will be equal to,
0.
yes, will be 0. So this green charges, let me call all of them green, 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 and green, 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 green. This green charge cannot create field outside. Only pink charges can create field outside. Do we understand this?
Sir.
Then take the reverse of this. Field inside will be only due to the charge in the cavity, and the pink charges cannot create field inside. Do we understand this?
Yes, sir.
Sir.
That is the third statement. Resultant field due to Q plus Q on S2 and any other charge outside S2 at any point inside of the conductor is 0. So outer charges cannot create field inside. Inside charges cannot create field outside. Do we understand this, or this has gone above our head? Sir, to gaya. This is gone.
Understood. Sir.
कच्चा पक्का हो पक्का पक्का?
Paka, sir.
Let's see how much of you have understood this. Can I present the question? This is from your favorite book. Now, if you have this favorite book, you can bring it into the class because there might be some questions which we'll be doing from this book. And what is the name of this favorite book?
H.G. Verma.
S.C. Verma. It's been long since I ever saw this book, but okay. So this is page number 139, question number 3. If you have that legendary book, you can use this, and this is the question from there. A thin spherical metal shell. Now remember, the best questions of this book are in the objectives. A thin metallic spherical shell contains a charge Q on it. So this is case number which? 1, 2, 3, 4. Which one? And a small charge Q is placed at the center of the shell. Another charge Q1 is placed outside on it as shown in the figure. All the three charges are positive. What is the force on the charge at the center?
Zero, sir.
Huh? 0, sir. That is the answer, sir. Do we understand this? Or it has gone above our head saying bye, 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 bye. Do we understand this? Huh?
Yes, sir.
Pakka? Kacha pakka, pakka, pakka.
Pakka, pakka.
Okay. So this is what we say application of what we have done. Then there is the next question which comes right after this one. And can I put it here only? Yes, let me put it here only. Tung tung. I can put it here. Let me put it. Let me delete this. Then it will come. This is better. So there comes this next question. Consider the situation of the previous problem. Previous problem is also there. The force on the central charge due to the shell is. I'll give you 2 minutes to give me the answer. Here we are and back. What is the electric field? No. What is the force on the central charge due to the shell is? The answer is very simple. The answer is very simple. I mean, the charge on the shell is Q. It is uniformly distributed. The force on the central charge would be 0. So the answer is 0. How many of you understand this? Everyone understands it, but democracy does not win. Democracy does not win. Logic wins. The correct logic is it is towards right. Now, why it is towards right? Can anyone now give me the answer? Someone said towards right. Why it is towards right? Cannot play akkar bakkar Bombay wo 80 90 pure 100. Why is the answer towards right? Now remember, there are two ways in which you can understand this. The force on this charge, central charge is 0. We all understand this? Yes or no?
Sir.
The force on this central charge is 0. But if I look at this pink charge, if the shell was not there actually, if the shell was not there, this pink charge would have repelled it and would have produced the force in the leftward direction. Yes or no? You take
Sir.
out this shell from in between. You take out this shell from in between. This pink charge would have repelled it. Yes or no?
Sir.
Just because of this shell, the pink charge is not getting repelled. Yes or no?
Sir.
That means this shell is doing something. And what is this shell doing? This shell is applying a force towards right, and so that the charge on the force on the charge Q becomes 0. Do we understand this? Yes or
Sir.
no?
Sir.
Now we have to understand how this is done. How can this shell create a field in the green direction? Now what happens? When this charge, if I forget this charge, when this charge is not here, let us forget about this charge. When
Zero,
this
sir.
charge is not here, and we will see it in the next class, because of this small q at the center, there will be a charge minus q coming on the inner surface. Yes or no?
Yes, sir.
Then there will be a charge q plus q coming on the outer surface. Yes or no?
Yes, sir.
If that outer charge is disappeared, this charge or any charge will be distributed uniformly because this is a uniform surface. Yes or no? We understand
Yes,
this?
Sir.
Sigma is inversely proportional to r. R is constant, so this charge will be uniformly distributed. Yes or no? But what
Yes, sir.
the gentleman is doing now, because of this charge, the charge on the sphere gets redistributed. Charge on the sphere gets redistributed. So this positive charge is actually repelled. Ding, 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 ding. Positive charge actually gets repelled. And near to that charge comes our negative gentleman, minus, 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 minus. If you don't understand it, minus, the charge does not get uniformly distributed. So the uniform distribution of charge goes away. So more charge, more positive charge will go towards the left side, and very less positive charge or even negative charge will come on the right side. Do we understand this?
Yes, sir.
And that is how the charge will redistribute in such a way that the net field created by this shell will be in the rightward direction, and that field will create this field. That field will cancel this field, and that is how the net force on the charge becomes zero. Do you understand this? And that is why whenever you have a charge placed in front of a conductor, the charge on the conductor gets redistributed. And that is the reason when I gave you question of these two spheres, I always told you the spheres are very far from each other. Why did I give you very far from each other? Why did I give it very far from each other? Huh? So that this redistribution does not happen, or this redistribution is very less. Do we understand this? It has gone above our
Sir.
saying bye bye, sir. Ho gaya bahut. Enough for today. We understand this?
Sir.
Sir.
That is the concept of electrostatic shielding, and that is how smart a conductor is. As soon as you place the charge on the conductor starts to get redistributed because it has to make the field inside the conductor zero. Conductor is smart. We have to be as smart as the conductor to understand what is happening inside the conductor. Conductor does not understand electrostatics. Conductor is just a conductor. It's a non-living thing. We are living beings. We understand electrostatics. So we should be able to find out what should be the direction. Yes or no? Yes or no?
Yes, sir.
On that note, I will end today's class. In the next class, we will move ahead with more properties and try to wind up this chapter as soon as possible. Maybe in the next class, we should be able to wind it up because I think it's a longer class, right? I think we'll be able to wind up and we'll do some certain questions which come on this concept. Take care. God bless all of you. Bye bye.
Thank you, sir.
Bye, beta.
Bye.